Okay, so today I'm going to make kind of rigorous what I have said yesterday, and the way to do that is to put everything in the framework of Loevner differential equation. So I will essentially speak today about Loevner differential equation. But before I do that, I would like to come back to what I was telling at the end, that is the Hidishow flow, so to rephrase Hidishow equation in terms of conformal mapping. And that will be the starting point of the Loevner differential equation. So I recall the Hidishow equation. So we have proven yesterday that this is driven by, let's forget about the twiddles. Okay, so we have a moving boundary for which the speed is given by minus. So it's a constant which will be pretty soon irrelevant. So the speed of the moving boundary is proportional to the gradient of the pressure, and the pressure itself is proportional to the Green's function. And G is the Green's function of, let's say, omega t. Okay, that will be the domain at time t, and with pole at the sink. Okay, for just one more quarter of an hour, the omega t will be a bounded domain, the sink will be a point of this bounded domain. After that, we will switch to the more natural setting of omega t containing infinity, the sink being not infinity. But for just the computations, it's preferable to put the sink at a finite point. Okay, so now the sink, let's call it Z naught, okay? And well, the Green's function of omega t is naturally connected with the Riemann map. Okay, so there is a Riemann map. Let's call it ft from say the unit. So this is the unit disk onto omega t, sending 0 to z naught, and such that ft prime of 0 is positive. Okay, so Riemann map theorem says that there is a unique map ft, so which is holomorphic and bijective, of course, sending 0 to z naught with a positive derivative at 0. Okay, so this is the Riemann map. So let's make a picture. Okay, so let's call points on the boundary of the circle. Whoops. If I fall down, it's not a big deal, but I'm not supposed to fall on this precious, valuable thing which is behind. Okay, so let's call point on the circle zeta, and here we have, so this will be e to the I theta, and then we have the point f of zeta here. Okay, which we call z. Okay, and then we want to compute a little bit so we have a tangent here and the normal derivative here. Okay, so the tangent, so this is the unit tangent, of course. So the unit tangent is given by I e to the I theta ft prime of e to the I theta divided by modulus of f prime of e to the I theta. Okay, and so the normal will be e to the I theta f prime of e to the I theta. So I multiply by minus I divided by modulus of f prime. So sorry being so. I just want to go into the computation to persuade you of the formulas. Okay, so this is n, and so this is also zeta f prime of zeta divided by f prime of zeta. Okay, So now G, what is G? G, of course, is minus log of ft minus 1. Okay. So this makes a pole exactly at the sink, and it is 0 on the boundary, and it is positive. Okay. So now P, the pressure, is Q times G. So let's call this U, and this is the real part of U plus IV. Okay, and now V is a multi-valued function, which is a conjugate to U, so which is so the real part of so it's minus Q, and then we have log ft minus 1 without absolute value. Okay, so this is a multi-valued function. Okay, so now gradient of P, just by Cauchy-Riemann formulas, this will be du dx minus dv dx. So this will so this is d dx of u minus iv. So this is d dx of u plus iv bar. And so this will be minus q f minus, so I differentiate this, so d dx or d dz will be the same. So we have minus, so f t minus 1 prime divided by ft minus 1 bar. And so continuing the computation, we get that this is, so ft minus 1 prime, we write what it is. So it's minus q divided by ft prime of ft minus 1 bar. Conjugate here. And so this coming back to the variable here, so it's minus q divided by zeta ft prime of zeta. Okay, so now we can compute a gradient of P scalar n, which is a normal derivative. So this will be the real part of, sorry, this is a bar here, okay. So it's a real part of the conjugate of that. So this will be minus q divided by zeta ft prime of zeta. That's gradient of P times n. So we will have here zeta f prime of zeta divided by modulus of f prime of zeta. Okay, so this cancels out. And so we have minus q over f prime of zeta. Okay. So and this is also by the initial equation. So this is also okay. So now v scalar n. So this will be okay. So I write. Sorry, I forgot about that. I write v scalar n from the definition. Okay, so v is d dt of ft prime. So what we get is, and I will put a dot to indicate differentiation with respect to t. So ft dot will be d dt of ft. So this will be ft dot of zeta f prime of zeta divided by modulus of f prime of zeta. So there is a bar somewhere. Sorry, I'm confused.
It should be in f prime of z.
Ft prime of zeta.
Yeah, so
What would you say?
Last factor should be with bar I.
Yeah. That's what. So this is here, and okay. Well, everything combined, we get that real part of ft dot zeta bar, ft prime of zeta bar. So this is minus q over, well, over f prime of zeta, maybe with a constant. So let's say q prime, okay? Because the constant will be this constant here, okay? We just identify this and that, multiply by a certain constant. Okay, and maybe there is a plus. Or maybe not. Minus q. Yeah, I think it's okay. No?
The denominator cancel.
Yeah, so you have is f prime on both parts, so
Yes.
it should be a constant.
Yeah, this is constant. Yeah, because I identify this with that, and the denominator cancels, so I have that. Okay, that's exactly what I have. And so multiplying here by zeta f prime of zeta on both sides, we get that well, I'll multiply here, so this is real part of ft dot divided by zeta ft prime of zeta, and then I have modulus of ft prime of zeta square, and this is a constant q prime. And so what I get is that real part of ft dot divided by zeta ft prime of zeta is positive in particular, okay? And the boundary ft dot divided by zeta ft prime of zeta on the boundary is equal to q prime divided by ft prime square. Okay, and so here we have a function, an holomorphic function with positive real part, and that and we know the boundary values of this of it. So actually we can write this holomorphic function as well, this is real part, as the Cauchy transform of its real of the real part of it on the boundary. So we get the equation, which is sometimes called Polubari-Nova-Galin. I think these are two mathematicians who were here, actually, in St. Petersburg. I think, at least they're Russian.
Galin is a name, and Polubari-Nova is a surname.
No, there are two people. These are two people. Okay, and Polubari-Nova was a lady, and she lived exactly 100 years. So from 1899 to 1999. Well, that's what I heard, so I don't know. So we have that ft dot of zeta is, so sorry about the signs, but I maybe have messed up the signs, and I'm not very good in computing on the blackboard. Okay, so sorry about that. But actually we should find minus zeta. I lost a sign somewhere. Q times integral over t of 1 over ft prime of e to the I theta square, and then I have e to the I theta plus z divided by e to the I theta minus z d theta. So this is just the Cauchy formula I mentioned. Okay, so it's how to recover holomorphic function from its the real part of its boundary value. Okay. So this is an equation, and this is actually we can also say that if we put mu t equals say Q is negative in our case. Okay, Q is negative. This is because we have a sink and not source. Okay, so actually, if we put minus Q divided by ft prime of e to the I theta square d theta, so we have a positive measure. So this is a positive measure on T, on the circle. Okay, and so we have the equation that ft dot of zeta equal minus zeta ft prime of zeta integral of e to the I theta plus z divided by e to the I theta minus z d mu t of theta. Okay, so and this is actually a Loevner equation. Okay, so I will come back on this. So this is a Loevner equation, except that here the measure depends on ft. So we have actually an equation. Okay. So what we will show now is that if we have a family of positive measures, on the circle, then actually this equation has a solution. Okay, and this solution corresponds exactly to a family of Riemann map to to an increasing family of domains. Okay. Now, Illy-Shaw equation relates to this Loevner equation, but it becomes an equation because the mu t depends on the solution ft. And actually, this equation has no solution in general, so it's an ill-posed problem. So we will have to get rid of that contradiction of this problem. Okay. Okay. Now, before I start with Loevner equation, let me come back to the nice situation. So now we switch. Oops. To the nicer setting. So what will be this setting? Well, actually, we want the complement of omega t. So omega t is is not an increasing family of domains; it's a decreasing family of domains because we have a sink in it. Okay, so so omega t shrinks. Okay, and now I want that the sink to be at infinity. So we put kt. So this will be an increasing family of compact sets. Omega t will be c bar minus kt. Okay, and now ft. So let's say that 0 is in kt just to fix the ideas. So the origin is inside there, and now ft will be the Riemann map from, let's call delta, which will be the complement of the unit disk, to omega t, which stands infinity to infinity, and which is such that ft prime at infinity is positive. Okay, so what do I mean by ft prime at infinity? Well, you have a map here. So this map has a Laurent expansion. This Laurent expansion has only one term of positive degree because it must be injective. Okay, so ft of z is something like, let's call it c of t, because this will be plus b0 plus sum from n greater than 1, bn divided by z to the n. So this is a Laurent development at infinity of ft of z, and we want, and c of t will be ft prime of infinity. So ft prime of infinity will be c of t, and we assume that this is positive. Okay. So in this setting, the equation becomes, well, I haven't written it down. So the equation now, so this is 1. So equation 1 becomes ft dot of zeta equals, and now we have zeta ft prime of zeta integral of, and then I have z plus e to the I theta divided by z minus e to the I theta d mu.
Z should be z. Well, z and z.
Yes.
You have too many there.
Yes, you're right. Zeta should be z. Then it's okay. Now it's correct, no? Oh, okay, and here also, sorry. Ah. Let's put this at here. And well, sorry. It's a little bit confusing. Yeah, all the time here. Oh, thank you. Okay, and then we have this equation. Okay, so now we are going to study this equation in this setting. Okay, which is a natural setting to study growth. Now the cluster, of course, is KT, and so this is a growing cluster, and omega t is a shrinking domain. Okay. So now what we are going to make a detour through this equation called the Loevner. So this is radial Loevner equation. For those who know a little bit about SLE, okay, so this corresponds to radial SLE. Okay, but in the setting of the complement of the disk instead of the disk. Okay. Okay, so now we are going to study this, and then we will correct this equation so that it has a solution. So this will be the Carlson-Makarov regularization. And then we are going to define all the objects I defined yesterday, which are Hastings-Levitt of order alpha and Healy-Shaw of order alpha. Okay, and to finish today, I hope, I will show that DLA is a probabilistic version of Healy-Shaw, or Healy-Shaw is a deterministic version of DLA. Okay, so that's the program for today. So about Loevner equation, I will not go into the proofs, so I just ask you, if you wish to see the proof, to go to my notes. And the proofs are there, and I think they are correct, because this is a chapter I have well revised. Okay. So now we go for the general situation. So we have KT, t greater than 0. So this is a growing family of compact sets. Okay, so this family, we assume, first of all, that KT is connected. And we assume that the complement of KT is connected, which means that KT is so-called full. Okay, there are no holes. Okay. Then for this family, as we have said, we can define omega t equals the complement of kt, and we have the Riemann map ft. Okay. So now ft of z, as I said, is c of t z plus terms, and c of t, which is the derivative at infinity, is also the logarithmic capacity of kt. Okay, so this is a definition. Okay, this is the logarithmic capacity of kt, and by Kerber theorems, it appears that c of t is equivalent in a very strong sense. I mean, this means between two constants which are actually 4. Okay, so it's equivalent to the diameter of kt. Okay, so that's of course because we can also define logarithmic capacity of other sets than compact sets. So, for instance, we could define logarithmic capacity of Cantor sets. Okay, and then this wouldn't be correct anymore. Okay, so this is only true because kt is connected. Okay, because it's a continuum. Now we make some more assumptions, because we want actually this quantity c of t to be continuous. And what does it mean geometrically on kt that c of t is continuous? This is exactly given by the Kara-Theodori topology. So we assume that omega t, now we look at the family omega t, the family of the complement, t is continuous in the Kara-Theodori sense. So that's equivalent to saying that c of t is continuous. And it's equivalent to saying that ft as a family of functions on the delta is continuous for the topology of compact uniform convergence on compact sets. That's in T for the topology of uniform convergence on compact sets. And this is equivalent to saying, so geometrically, it means that two things. So continuity means continuity on the right and on the left. Okay, and the continuity on the right and on the left is equivalent to two things. So first of all, for any t0, omega t0 is the union of omega t for t greater than t0. So this essentially means that there is no jump in kt. Kt never suddenly grow. You can never add a line or something suddenly. And so this is the right continuity and the left continuity. So this is only for t0 positive.
So, in the Kara-Theodori sense is the Hausdorff topology.
No.
Between the
No. No, let me show you an example just after. No, this is very different from the Hausdorff convergence of the topology in topology for KT. Let me show you an example later. Okay, I just finish here. So for the left continuity is a little bit more difficult, and that's precisely because of your question. Yes?
Could you read the last two statements? 4 lines, yes.
Sorry, what is the question?
I can't read the last
Oh, you cannot read. Okay. So continuous in the Kara-Theodori sense, I give 3 definitions of it, and they are equivalent. Okay. So first, C of t is continuous. Ft is continuous in T, so it's a. So you look at the map T gives Ft, okay, and you equip the target space with the topology of uniform convergence on compact sets. Okay? And this is equivalent to the geometrical, so the geometrical meaning of Cartesian convergence is this one. First of all, for any t0, omega t0 is the union of omega t for t greater than t0. Remember that omega t is decreasing. Okay. And for any t0 positive, omega t0 is the complement, the component, sorry, the component, the connected component of the interior. So look at intersection of omega t less than t0 takes the interior containing infinity. So so in some sense, okay. So maybe in the Cartesian convergence, you need to specify a point. Okay, the point here is infinity. Okay, so maybe it's a little bit. If I want to show you a counterexample, it's better to show you an example in the Cartesian convergence for another point. Okay, so let's consider, for instance. Let's take a. So let's put. So this is 0. So think of 0 as being infinity. Okay, and then take a domain which is. Let's take a big disk. Well, a disk here and a very small, narrow gate here and another disk here. Okay, and let's close this. Let's close this this thing. Then the convergence in the Cartesian setting. According to 0, will be just this part here. You will forget all these things, which can be extremely big, but with very small harmonic measure. The probability from here, Brownian motion to come here is very small. So you can just, so it will die. This big part will die. Okay, that's Cartesian convergence. So it is not convergence on the boundary in the sense of Hausdorff. Definitely not.
Convergence with respect of the.
Yes. So here I do not specify the point because it's a very specific point at infinity. But I should have, if I want to define it generally, I should define a point. Of course, the conformal map should send 0 to 0 here. Okay. So that's the point 0 is very important. Okay. So. So we have this setting, and then we have this thing. So C of t now is an increasing function. So it's actually increasing. Okay, so it's strictly increasing, and we will assume furthermore. So this is not a big assumption. This is just to give a nice framework. So we assume further that. C of 0 is 1, and that C of t goes to infinity as t goes to infinity. Okay, so that means the cluster the diameter goes to infinity. Okay, now changing time, we may assume that C of t is e to the t. Okay, which is a okay. So that will be the specification we will make. Now we look at the family Ft, and now the fact that KT is a growing family translates into the family ft in the following sense. It translates into the fact that we can define HST, which will be fs minus 1 composed with ft. Okay, since omega t is included in omega s, this map is well defined. So we have a well-defined, so this is a kind of a resolvent in a resolvent family. Okay, so it's a well-defined family of holomorphic maps from delta to delta. Okay, and so we write this in the sense that fs composed with hst is equal to ft. So ft is fs composed with something, so we say that ft is subordinated to fs. Okay. So now we can make a definition. And so we say that a Loevner chain, so it's a family ft of z of function holomorphic in delta, which is like e to the t z plus etc., which are injective, and such that ft is subordinated to fs if s is less or equal to t. Oh, okay, I didn't say that, but s, of course, is less or equal to t here in order to make sense, this to make sense. Okay, so I have a family of functions which are subordinated to each function is subordinated to a function of time with time smaller, and they are all injective, and they all start by e to the tz. So this is called the Loevner chain in the classical theory of Loevner. I mean the original theory by Loevner, which goes back to the 20s. Okay, so now the important thing is the following theorem. Before I state the theorem, let me define an important class which we have already met this morning. So let's call P of delta. This will be the set of function P from delta to C, which are holomorphic at infinity with value 1 at infinity, and which has positive real part. Okay, so this is a definition. And now we have the theorem, which is, for instance, a basic starting point for the SLE theory, if in some sense. So first of all, so we have two parts in this theorem. So if ft is a Loevner family, a Loevner chain, then, so as we have seen, ft is by definition continuous in T for the topology of uniform convergence. So actually we have much more. The simple fact that it is continuous will imply that it is actually absolutely continuous. So ft, T gives ft of z is absolutely continuous. So with respect to Lebesgue measure, it's actually even Lipschitz. Okay, it's more than absolutely continuous. It's Lipschitz with respect to Lebesgue measure for every z in delta. Okay, and there exists a family P T greater or equal 0 in P of delta, measurable in T. So there exists a measurable family of functions with positive real part, such that almost everywhere ft dot is equal to z ft prime of z pt of z. So this is exactly the same equation as I've written before, okay, for Healy-Shaw. For Healy-Shaw, pt of z was just the Cauchy transform of this measure mu t that I've been written that d theta over ft prime square. Okay? So this is a very general feature. If you have a Loebner chain, then you have such an equation. Okay? So this is actually not a differential equation, it's a PDE, it's a partial differential equation, but a very simple type because it's linear of order 1. Okay, so let's call 1 this equation. And now, of course, the strength of Loebner theory is that we have a converse. So conversely, given measurable family Pt in P of delta. So here we need absolutely no regularity in T. That's very striking. Except measurability, which is kind of really mild. And phi from delta to C holomorphic and injective. Think of phi being identity, for instance. Okay, that would be the nice, the usual situation. Then there exists a unique family, Ft. There is a Loebner chain. Oh, okay, holomorphic and injective with phi prime of infinity equals 1. Solution of 1 with f0 equal phi. Okay, so we can solve the equation. We can solve this equation with boundary value f of 0, f0 equals phi. So I will not prove this theorem because this is quite lengthy. I mean, but give just a few ideas about the proof of this theorem. So of course, when I mentioned SLE, well, in SLE you choose as a family PT just the Cauchy transform of Dirac mass at lambda of t, where lambda of t is e to the I square root of kappa bt, where bt is Brownian motion. Okay, and then you get this, and this will be, well, this will be radial SLE in the outer outside of the disk. So we will apply this theorem, but for, of course, different PT, different family. Okay, so how do we prove this theorem? So the first step is to prove that we have absolute continuity. So this is a very technical thing, but very straightforward. It's just a consequence of known distortion theorems for univalent functions. Okay, so it's essentially Koebe, but you must apply Koebe kind of 10 times. Okay, and you get that. You get absolute continuity in T. Now, to show this, well, this is not very hard. I mean, but it's even very intuitive, because if you look at the quantity ft dot divided by z ft prime, so this is essentially as we have seen before, this is essentially well, saying that if t dot divided by z f t prime has a positive real part is the same as saying that if you look at the moving boundary, the normal speed, the normal velocity makes an acute angle with the normal. That's what it says. And this exactly says that the moving boundary is decreasing. So the fact that it is a moving boundary of a decreasing family of sets exactly translates into the fact that the real part of this divided by this is positive. Okay, so I switch the details. Of course, if you, the real proof doesn't do that, but the real proof you don't see the intuition. Okay, the real proof goes through the subordination, but it's the same. So this is easy. So the first part is easy. Now the second part is much more involved, but the idea behind is very simple. So the idea behind is to write the equation for ft minus 1 in some sense. Okay, and then this becomes a real differential equation, and we solve this differential equation using, well, Cauchy-Lifshitz theorem. Okay, so let me just outline this. So to prove, idea of proof of 2. So we look at the function s gives hst. So this will be defined. So first of all, we suppose that we have we go by we first suppose that that we have a Loevner solution. We find something and then we go back. Okay, so we prove by analysis and synthesis. Okay, so by analysis, if you have a Loevner chain, then you have this map here, S gives HST. This is defined on 0t. Okay, and if you differentiate this, and it satisfies the ODE d omega over ds is minus omega ps of omega. Okay, so if you differentiate HST with respect to S, so I don't do the computation, so this is done in the notes, but it's very straightforward. Using this equation, you get that we have this. So this is an ODE. Okay. And so this is if we so now if we want to prove 2, so we don't have the ft, but we can start with this equation. So to prove 2, we start with this equation, and we solve it. Okay, we solve it at with initial point t, and we solve it with backward time. The s going from t to 0. Okay, so the initial point will be at t, and we look at. So the problem is that this equation may blow up at some finite time. So it may not be it might not be defined for all time until 0. So to prove that actually it does, we use the fact that if you look at dw modulus square over ds. If you compute that, you get that this is minus 2 modulus of omega square, real part of PSW of omega. Okay, and this is negative. So sorry, this is minus, and this is negative. Okay, using that, because real part of PS is positive, of course. Using that, we get that this is automatically, because the only way that this equation blows up is that we go to the boundary. But here, since it is negative, omega is, well, maybe it is plus here. Well, I have problems with sign. Okay, so maybe this is positive here because we. Well, I don't remember. Well, the fact that this real part is positive exactly means that this equation cannot blow up. So this equation is defined for all time. And so we can define omega of S T Z. So that will be the solution of this equation with value Z at time t, and which is defined on the interval 0, t. Okay? Now, this is holomorphic in Z by just general theorems, because everything is holomorphic in this equation. And moreover, it is injective in Z because of the Cauchy-Lifshitz theorem, the uniqueness of solutions of the equation. Okay? And now it suffices to to write down ft of z. So the solution will be phi of omega of 0 t z. So that will be the solution to the equation. Okay? So that's the idea of the proof of the theorem. Okay. So again, sorry about my confusion with signs, but everything is written in the notes. Okay, now let's come back to P of delta. So P of delta is the set of function with positive real part. Now this set of function has a representation called Herglotz representation. So Herglotz representation theorem so P of delta is precisely the set of function P of z of the form integral over t of z plus e to the I theta divided by z minus I theta d mu of theta, where mu is a probability measure. Well, actually, if mu is a positive measure, then P has positive real part. And if you add the fact that it is a probability measure, you get the condition that P of infinity is equal to 1. Okay? Which is just a normalization. Okay, so now, so if you have any family of probability measure, you get a growth process, and any growth process gives rise to a family of probability measures. Okay, so that's the Loevner philosophy. Okay, to reduce a 2D growth process into a 1D family of measures. Okay, so it simplifies. The geometry is simplified by. So the geometry is replaced by analysis. That's a philosophy. Okay, so let's see a few examples here. What happens if we take examples? So let's consider, first of all, the simplest possible case. We take as a measure mu t for every t. So mu t will be constant in t, and we take mu t to be, well, ds divided by 2 pi. Okay, so the uniform length on the circle. Okay, so what do we get as a process? So the equation now becomes ft dot. Loevner equation is just ft dot equals z ft prime. Okay, and the solution to this is obvious. It's just ft of z equals f of e to the tz. f0 of e to the tz. So this is the growth by equipotential. Okay. Kt will be just the the domain inside. So it will be the domain G less than T. Okay, where G is the Green's function. Now, in some sense, Polu-Barry-Nova-Gallien equation is close to that, because Polu-Barry-Nova-Gallien equation is d mu t equals ds over f t prime, well, d theta, I guess, f t prime of e to the I theta square. Okay. So in some sense, it's a little bit like growth by equipotentials, but of course, this quantity may blow up or be close to zero, and this, of course, will change drastically the growth. Okay, so this is well, very simple example where mu t is actually absolutely continuous with respect to Lebesgue measure. Now, on the opposite, of course, is the case where mu t is a Dirac mass. Okay, it's completely singular, and the most simple singular thing is so that's Polu-Barry-Nova-Gallien. Well, just a comment about. Sorry, I come back to Polu-Barry-Nova-Gallien. This is of course not a probability measure. Okay, so this is not a non-normalized Loevner equation. So in general, if you have a non, okay, so this is a remark. So if you have an equation ft dot equals z ft prime integral of z plus e to the I theta divided by z minus I theta d mu t of theta, where mu t is not supposed to be a probability measure. Well, then you still have a solution, and actually you have ft of z equals c of t z plus etc. And now c of t solves c dot of t equals total mass of mu t, c of t. Okay. So when total mass of mu t is equal to 1, we get exactly exponential t, and in general we get c of t solving this equation. So this is just this is not important, but I mean we will use it. Okay, so now conversely, so I don't have time, unfortunately, to detail the computation, which is not so easy, but suppose that mu t is again constant, but Dirac mass at a point. Okay. Well, so this is in some sense orthogonal to the growth by equipotential. So now instead of a growth by equipotential, we will have a growth by external rays. Okay, that means that if we start with phi being mapping to a domain here, then if we have zeta here, what we will, and we have phi of zeta here, the growth will be the growth of, so we have here the ray here, which correspond to a, that's what I call an external ray. It's just the image by the Riemann map of the ray starting from here to infinity here. Okay, so I will have a growth along, so I will just add to this initial cluster a piece of the external ray. So now the question is, what piece? Okay, until when I go there, and this is well, then you have to do the. So I skip the computations. So I just state the result. This is again in the notes, because I would like to finish with the Carlson-Makarov-Ilishov. So if you have suppose you have that phi t dot equals m times. So I add a constant. So I do not normalize things. So I use something like this here. So phi t dot phi t prime z, and then z plus 1 divided by z minus 1. So I just take zeta equal 1. If I take zeta equal 1, then of course here integral of z plus e to the I theta divided by z minus e to the I theta d mu t is just z plus zeta divided by z minus zeta. Okay. Because we have that. So we have the equation here. So it's a non-normalized Loevner equation with this. So what we know is that this grows. And suppose also that phi 0 is identity. And we want to know how far we go along the external ray. Okay, but and this is exactly given by the square root. So phi t will map the complement of the disk to the complement of the disk minus the external ray starting from the point 1 here and going to 1 plus 2 square root of mt. So it's essentially square root of this. This is not exact. Okay, this is about that. And this is, well, it's about that. And this, this quantity is just valid for t small. For t big, it wouldn't be correct. Okay. So actually, the exact value is quite involved to compute. And bizarrely, it is not easy to solve this equation. So one has to go backwards, and so one has to use well, some kind of very easy Schwarz-Christoffel argument to prove this. But then you have a long, lengthy computations. But what we have to recall here, and that will be important for what I will say now, is that if you go in time t, you essentially go square root of t out of the circle, at least for t small. Okay. So now let's come to regularization of Ilishov. So this was proposed by Carlson and Makarov. So again, Ilishov flow is an ill-posed problem. It has no solution. So we have to do something in order to get solutions. So the idea is the following. So let's put a definition here. So let phi from delta to c be holomorphic injective with phi of infinity is infinity. Okay. So phi maps the complement of the disk to the complement of some set. Put a point zeta here, and then we have phi of zeta here. And now start external ray here, and this goes to an external ray here, and we will define, so we defined epsilon of zeta phi as being the infinimum, of t positive, such that the distance from phi of 1 plus t zeta to d omega, so this is omega. Omega is the exterior, is equal to delta. So we fix a delta, which you may think of being small, And then what you do is that you travel on the external ray. That means you travel here until the first time you get far from the coast. Okay, so traveling here means going outside of this island here, and you just travel just enough so that you reach the international zone in the sea. Okay, so that you get out of the country. So it is the first time that you reach distance delta from it. Okay, so it essentially means that the object you add here is of size delta. Okay, so that's maybe start to be reminiscent the DLA here. Okay. So by Koebe theorem says that the distance from Koebe theorem says that the distance from phi of 1 plus 1 plus epsilon zeta to d omega, this is equivalent to, again, this equivalence is a very strong sense, to epsilon phi prime of 1 plus epsilon zeta. Okay, and this is equal to delta by no, not this, but this. Okay, so it means that phi prime. So it means that it means that epsilon is essentially delta divided by phi prime of 1 plus epsilon zeta. Okay. So this is not the derivative at the point zeta, which would be the case in the genuine Elie-Shaw flow, but this is phi prime at a point slightly inside the domain. First of all, this is now defined, because the derivative at the boundary is not defined if the boundary is not smooth, and it is more robust in some sense. Okay? So now we replaced Elie-Shaw. So I recall that Elie-Shaw was mu t. So Elie-Shaw was mu t equals ds over f prime of zeta square. Okay. And now we have regularized Elie-Shaw. We take mu t equals, we just take epsilon t square ds. So epsilon t will mean epsilon with phi equals ft. Okay, and we take a square because what I just said about here. Okay, so that the object, so that the length of the path here is about delta. Okay. And now this is an equation that you can solve. So this is now well posed. Now to be totally sincere, this is well posed. Well, I guess that if I wanted to prove that, I could using some kind of very general theorem like Kovalevskaya theorems about PDEs. But I don't know any simple proof of that. So if you have some, I would be glad. Because Carlson and Makarov, they just say nothing about this. They just say, this is well posed, okay? And when I asked them, they said, oh, this is obvious, okay. So. Well, I guess it is obvious, but I don't know exactly how. Okay, So this is now regularized Illy-Shaw. Now to finish with, let me define now a version of DLA associated to that. So now a version of DLA. And then I will define, well, let me define that, and then tomorrow I will come to the Hastings-Levittov and Illy-Shaw alpha. So let's consider xi. So this will be a sequence of IID, so independent random variables with the exponential law of mean 1. Okay. Now I define tau I as being x1 plus xi. Okay. So these are exactly Poisson times. Okay. And I defined mu t. So now I define the measure mu t as in the Loevner setting. I define mu t as being epsilon s square of zeta. Sorry. Epsilon tau j, tau I square of zeta I. Dirac mass at zeta j for t in the interval, say tau j, tau I plus 1. Okay, so it be
I and j.
oh, so I. Sorry. So what are zeta I? Well, zeta I is a sequence of independent numbers chosen with uniform law on the circle. Okay, and this is also, of course, independent of the xi. So everything is independent. So we have that. So essentially, between times n and then between times I and I plus 1, I choose this. Okay. So this means that between these two times, which is essentially of length 1, so the time length is 1, I have this thing. So it means that I add an object which is precisely of fixed size delta.
For the next interval, I choose new zetas, right?
New what?
New zetas.
Yeah, of course. Yeah. Zeta I is a sequence of yeah, of course. I choose at random theta each time. Okay, and so this will be a version of DLA. Okay. Now, if you look at the expectation of integral from t to t plus delta t of mu s of, say, a set. Let's take a Borel set on the circle. You look at mu s of A and you integrate this knowing what happens at time t. Okay, what you get is something like, because of the Poisson situation we have here, we get delta t times integral over A of epsilon t square of zeta d zeta plus lower terms. So dividing by delta of theta, you see that essentially in the mean, when you consider this situation in the mean, what you obtain is Illy-Shaw. So in some sense, Illy-Shaw appears as a deterministic version of DLA. Another way of saying that is that if you look at this process, you let delta go to 0, and you speed up the time. Instead of taking time 1, you take time, say, the delta, for instance, a very small time. So you add objects very rapidly, but very small. Well, at the limit, you get Illy-Shaw. That's the idea. So that's the connection between DLA and Illy-Shaw. So if you allow me 15 seconds. So tomorrow, I will define similar things. So we can define similar things with replacing epsilon square by epsilon to the alpha. So then we get Illy-Shaw alpha, and here we can do the same, and we get Hastings-Levittov alpha. Okay. and then we will study what happens. And so tomorrow, I mean, the fact that we have replaced derivative by this will allow us to use multifractal properties of harmonic measure to study growth of the objects. So that's for tomorrow. That's a program for tomorrow. Okay, so sorry for the delay. Sorry.